Hello, good morning, everyone. Today we have a thesis dissertation, which is title is Epitaxial Growth of Complex Oxide Thin Films and Heterostructures for the generation of spintronic devices. It's going to be presented by Sulong Chen from Institute of Materials Science in Barcelona. This thesis has been supervised by Professor Benjamin Martinez and Dr. Narcís Mestre. Before starting, let me introduce the evaluation committee. First, Libertad Abad is going to act as vocal and also secretary, and she's from Microelectronics Institute of Barcelona, next door here, and also belongs to CSIC. And then another member of the committee is Regina Galceran from Universitat of Barcelona, and I am Javier Palomares from Institute of Material Science in Madrid. So, well, the hard work is already done, so relax and try to summarize the main results in a reasonable amount of time. Okay, thank you.
Thank you for the introduction. Okay, and today, hello everyone, and welcome to my CSIC defense. And today I'm going to introduce my topic, and I'm from the PhD Material Science program in UAB Cooperated, and my supervisor is Professor Martinez and Dr. Martinez. And my topic today is going to introduce is epitaxial growth of complex oxide thin film and heterostructures for the next generation of spintronic devices. Okay, let me introduce some basic motivation. As we know that as increasing of the information technology, and there's a huge amount of the energy in consumption. And for example, the ICT sector, the information communication technology, by 2020, it cost 1/10 of the electric consumption than the total electric generation. And it's also the data center cost more electricity than most of the countries. And however, with the arrival of the artificial intelligence, this situation is even worse, and it's adding more electricity demands. For example, as a single the ChatGPT query is caused 10 times larger the energy consumption than the Google search, and it's also cost more electricity than some of the lowest consumption countries. If we look at the proportional of the energy consumption from the GPT query, for example, here we saw that there's a most proportional is coming from the computational processing. It's occupied almost 75%. And so it's quite urgent and necessary to improve the energy efficiency of the current electronic devices. So we propose that the spintronic can offer a technology alternative since it explores the spin property of electrons alongside their charge to achieve the high performance information storage and processing. And it also a new paradigm for the development of the multifunctional electronics that combines the logic, storage, and communications while improve the energy efficiency. Let me introduce some basic concepts. And the spintronic utilizes a pure spin current. It's a kind of a coherent propagation of spin angular momentum without the net flow charge involved. So in this way, it could avoid the great problem, the heat dissipation. However, it's not a conservative quantity, and the decay is in order of the so-called spin diffusion length. And is a kind of very important parameters. And the key field of the spintronics is spin charging conversion. And this process can be achieved by the spin Hall effect and inverse spin Hall effect. Where as we showed in this figure, where the spin Hall effect, you could achieve from the charge to spin conversion, where apply the longitude charge current in this direction, and the charge spin, charge spin are separating in both directions, and then generate the pure spin current. While the inverse spin Hall effect is once inject the spin current in along this direction, it could as the charge current will accumulate along the one direction and generate electric field and generates the charge current. So it's a contrary phenomenon. And this spin to charging conversion can be expressed by this expression. And here the spin Hall angle is quite important parameter, which is an indicator of the efficiency of the spin charging conversion. And also there's a lot of ways to generate the spin current. For example, in this figure, the spin band splitting, thermal gradient, and the spin orbital effect, and so on. In our case in particular, we are utilizing ferromagnetic spin pumping, where the processing of the magnetization in the magnetic field and generate the pure spin current that flow into adjacent layer in the normal metal. Okay. And as I mentioned before, it's very important of the spin orbital coupling in the spintronic because it's coupled the charge and spin, allowing the spin charging the conversion process detectable through the spin Hall effect and inverse spin Hall effect. And it also connects the spin degree of freedom of electrons with their surrounding environment. So in our case, we need to achieve the high efficiency of the spin to charging the conversion. So we need both strong spin orbital coupling and large Hall angle. And the material choice is, for example, like the 5D element of heavy metal, platinum, tungsten, titanium, and iridium. In this figure, we show that the spin orbital coupling is strongly dependent of the atomic number, where the 5D elements show the relatively larger atomic number corresponding the relatively larger spin orbital coupling. And also another alternative is the oxide, like strontium iridium oxides. Then another important factor is to achieve the larger spin diffusion length. So it's quite important to utilize the low Gerbe damping materials. In the metallic material, typically utilize the parapermalloy, and oxide, for example, the EX binode and LSMO. Why is very interesting for us to utilize the transition metal oxide? Because it has a competition between the charge orbital and lattice degree of freedom, and it also have a highly tunability of the electronic structures at the interfaces, for example, at the local symmetry breaking, charge transfer, and so on. So it's provide a wide range of the options for tuning their properties. So our scientific motivation is to investigate oxide-based materials with potential application for the implementation of the spintronic devices. To achieve the high efficiency of the spintronic device, we need to achieve the efficiency of the generation, the spin current generation, and spin transport, and the detection of the spin current. Since the spin current transport is efficiency in high sensitivity to material property and interfacial characteristics, and also the complex oxide, which reach all correlated phenomenon and structure tunability, which could offer a unique platform for engineering spintronic device. In our case, we utilize the oxide structure LSMO, lanthanum strontium manganese oxide, as a spin injector. It's a very famous oxide material, and it has highly saturation magnetization and Curie temperature above room temperature. And also the magnetic phase can be tuned by the substitution level of the strontium. And also it's very important to improve the spin current and the transport at the interface. So we adapt the nucleoside on top of the LSMO to achieve the interfacial engineering. The material choice, we are utilize typical antiferromagnetic material, nucleoside, which it has a relatively high Néel temperature, well above room temperature, and also relatively simple FCC structures. So the scientific challenge is to investigate how the intrinsic material property and the interfacial properties influence the spin current transmission in complex oxide-based heterostructures. So our outline is to first, I will give the experimental section. then the results and discussion, and then to give the conclusion, outlook, and finally the acknowledgement. So first, let me introduce the basic material preparation. We are utilize the IR sputtering technique, where apply the high voltage and bombard the argon atom will it will be generate the globe discharge, and the argon ion will be bombard the target and inject the atom target. So the target atom and homogeneous evaporate on the substrate. In this case, we are utilize the on-axis and off-axis. Where the on-axis, the substrate is faced on the target, and where the off-axis, the substrate will be rotated to 90 degrees and move forward a little bit from the central axis. And the material will grow of these three layers, where the LSMO, nickel oxide, and platinum heterostructures, where the thickness, corresponding thickness is going as these figures. And growth conditions, we are utilize LSMO at 805 degrees, 500 degrees for the epitaxial growth, and then the nickel oxide we are choosing at room temperature for polycrystalline, and 500 degrees high temperature to achieve the epitaxial growth. And the platinum we are utilize at room temperature. So first, I will optimize the LSMO growth with on-axis and off-axis. Growth on the STO001. We grow the identical thickness around 15 nanometers of LSMO, and calculate by the X-ray reflectivities. And the theta to theta curve shows a very clear LSMO single peak without any other impurity phase, and also the low roughness surface obtained by EFI image. The Redis-based Spokal map shows the LSMO and the STO have the relatively similar implant parameters, indicating the coherent Foley string and growth on top of the STO. However, the DC magnetic property is quite different, where the magnetization and the TC is relatively higher on the with the off-axis. So we are utilize off-axis growth the LSMO with to achieve the higher magnetic properties. Then I optimize the nickel oxide growth. First, I grow the identical thickness around 25 nanometer again, with changing the temperature from 300 degrees to 600 degrees, and with increasing the temperatures, the nickel oxide peak shift to a high angle, indicating the lattice shrinkage with the lower oxygen vacancies, and also the lower surface roughness also attaining at 500 degrees. So it could achieve the optimal smooth growth at 500 degrees. So we choose this temperature and then growth other thicknesses like 3, 5, and 10 nanometer, and also obtaining the thickness from the reflectivity, and then calculate the thickness dependence of with the time, and get the calibrate the deposition rate to grow the other thickness while tuning the sputtering time. And then I grow the LSMO nickel oxide heterostructures. As a growth method, we choosing the 3 ways. For example, the in situ on-axis, the in situ off-axis, and the ex situ off-axis, where the in situ is to grow the LSMO nickel oxide and platinum without takeout from the sputtering chamber. And the ex situ growth is growth first LSMO, and then to take out from the chamber to pre-check the structure and the magnetic property, and then to grow the nickel oxide and platinum again in the sputtering chamber. Okay. So here we show the red curve of the in situ off-axis. Here shows the silver peak due to the globe. We fix the substrate on the heater, have some contaminant on the surface. So we also measure the magnetic property of the exchange bias with 3 ways. It shows the relatively similar exchange bias values, indicating the similar interface coupling. Quality is quite similar, and also the empty curve shows the off-axis relatively higher than the on-axis growth. Mimics the previously discussed the LSMO growth, where the off-axis is higher magnetic property than the on-axis. And also the roughness is shown quite similar from the EFM image. So regarding to better investigate the LSMO magnetic property, we are choosing the axial growth with LSMO off-axis and then to growth nucleoside and platinum with on-axis. And finally, I will grow platinum with on-axis at room temperature. Here shows growth of series of thickness, and the peak shows a very identical platinum peak. Then we also calibrate the thickness versus sputtering time and get the deposition rate again. And also the relatively flattened surface from the EFM image obtaining as well. One thing I need to mention that the platinum growth on the polycrystalline nucleoside structure will be a polycrystalline, while the platinum growth on epitaxial will be a textured growth. Then I will introduce some concept of the ferromagnetic resonance and spin pumping. In the real measure in this figure, we are face down the sample and contact with the coplane waveguide and excite the RF field along this direction and sweep a magnetic field along the perpendicular direction. And when the magnetic field, when the magnetic material absorb the energy, reach the resonant condition, and the ferromagnetic resonance dynamic can be expressed by the LLG equation, where the containing the steady state precession and the dissipation damping. Where the steady state, the first term is the laser magnetization processing around the effective field, while the second term is to let the magnetization close to the effective field. So once the magnetic material absorbs the resonant field, it will be calculate the derivative absorption peak in this figure, and this line can be described by the following equations. And also there's also have the relation between the resonant frequency and the resonant field can be expressed by the Kittel equation. And also the resonant line-wise containing the three components. For example, the intrinsic is coming from the spin orbital coupling, and the extrinsic component coming from the magnetic inhomogeneous and two magnon scattering. And also there's also a spin pumping at the interface. So we are prepare the two sample to comparison, where the single LSMO and also the nucleoside and platinum adapt on the single LSMO layer. In this case, we can extract the magnetic damping from the linear equation, and also the increasing of the magnetic damping or the delta alpha increase relative with single LSMO reference layer is a kind of an indicator of the spin current transfer through the nucleoside and absorbed by the platinum. So in our case, we are measure the magnetic damping of the three layer, where the damping is increased, clearly increased than the single LSMO layer. So it's indicating that the spin current is absorbed by the platinum. And let me introduce the inverse spin Hall effect. As I mentioned before, once the magnetization excites the spin current and transfer the antiferromagnetic layer and reach the normal metal, and it could be achieved the detectable electric the voltage via the inverse spin Hall effect. And the real measurement, we can measure simultaneously the inverse spin Hall effect voltage and the ferromagnetic resonance field, the absorption peak. And in this case, we are showing that the resonant field is quite similar, is in the identical position. We're showing that the inverse spin Hall effect is from the spin pumping. And the inverse spin Hall effect voltage, the line shaping can be described by the Lorentz function in this function below. However, there's also additional voltage contribution from the such as the spin rectification effect or the thermal effect. So it's important for us to separate this effect. What we do is to, by fitting the inverse spin Hall effect voltage, where the fitting is fully symmetry signal, while the spin rectification effect having the symmetry and the anti-symmetry component. So in our case, our data show that the inverse spin Hall effect is quite a fully symmetry curve with a negligible anti-symmetry component, indicating there's almost no spin rectification effect. And also we are reversing the magnetic field and measure the voltage is quite identical on amplitude. So indicating there's no thermal effect as well. In the real measurement setup, this is showing in this figure, and the facility is showing as below. It is listed as below, and the real measurement face down the sample and contact with the coplanar waveguide, and simultaneously measure the inverse spin Hall effect and ferromagnetic resonance curve. And here we go to the research log line. Our motivation is to achieve the high efficiency of the spintronics. So we need both the high efficiency of the spin to charging the conversion efficiency and also the long spin diffusion length. So what we do is first to optimize the LSMO to achieve the efficiency spin injector. What we do is to optimize the LSMO microstructure and its symmetry. And also, we also adapt the nucleoside between the LSMO and platinum layer to improve the spin current transmission. What we do is to optimize the nucleoside structure and also the magnetic properties. And finally, we compare the spin current transport through the polycrystalline nucleoside and the epitaxial nucleoside with different orientation. So our topic is going as this four topic as follows. First, we are growth series of the LSMO on top of the STO001 is to reduce the magnetic damping via the twin domain control to enhance the spin injection efficiency. And second, we are utilize strain relief in the epitaxial nucleoside film and to show how the nucleoside microstructure and the magnetic property influence the spin transmission. And the third and fourth work to study the spin current transport in the polycrystalline and the epitaxial nucleoside on both orientation, on different orientations. We study the dynamic. So before to study the dynamic magnetic property or LSMO, we need to find the find the real relation between the dynamic property and the LSMO structure. So we grow a series of the LSMO on top of the STO001. We show that the X-ray, the CO2 sector curve shows the LSMO peak, a clear LSMO peak regardless of the sample, and also the thickness is from the 10 to 15 nanometer. And also the EFI image show a quite clean, and the surface is terry-like surface with very low roughness and really similar of the miscut angle as well. And also the DC magnetic properties is quite identical on the series of sample growth on the STO001. However, there's a sample A in the low field shows a different kind of the line shape compared with other samples, with indicating a slight anisotropy absorbed different with other samples. So above this analyzation and like the structure and the magnetic properties, there's almost no change. So the dynamic property changed of the LSMO maybe come from the other factors. We are measuring the electron backscattering image from the SEM, where the sample A shows the microstructure of single twin domains, while the B, C, D, E, this sample shows a two in-plane orientation on twin structures. So what are they caused? It's due to the relatively low symmetry of the LSMO with Romhedro. Have to adapt on the STO with high symmetry with cubic structure. It will be performing the twin structures. And the twin's boundary density and the orientation is dependent on the growth parameters, such as substrate miscuts, surface terminates, and the growth temperatures. So it shows distinctive samples where the sample A shows a single twin domain, and the D sample shows the in-plane 2 orientation of the twin structure. We measure the ferromagnetic resonance along the 100 and 010 orientation, where the sample A shows distinctive of the resonance field, where the 100 relatively higher than another. However, the sample D shows the resonance field is quite similar. So it's indicating that the single twin structure have the uniaxial anisotropy along the 100 orientation. And also I measure also the resonance line wise, where the A sample shows a relatively narrower resonance line wise than the sample D. So it's indicating the dynamic magnetic damping is coming from the pinning effect from the as the twin boundaries. And so we also extract the magnetic damping on the series of the samples, where the sample A shows the minimum of the magnetic damping. And the magnetic damping also increased at the increase of the perimeter densities, where the perimeter density is the density of the twin structure or network. So we can conclude that the fewer twin boundaries which could lead to the lower magnetic damping. And one thing we can conduct that if the LSMO grows the 101 orientation, it could achieve the twin-free structure. So it could achieve the low damping as well. So first, we have studied the LSMO and nucleoside interface with the polycrystalline nucleoside structure. We measure the theta to theta curve, so there's no nucleoside peak from the theta to theta curve due to the limitation detection. And also we have grown a relatively higher thickness around 100 nanometer with 2D detection. The 2D detection, we show the nucleoside 002 have a preferential along the 002 orientation. And also there's integration curve, so there's both nucleosides peak. There's a nucleoside 101 and nucleoside 002, indicating the polycrystalline structure of the nucleoside. And also the device surface obtaining from the EFI image, also obtaining the flattened surface as well. We also measure the Hartf image or cross section, and also the EDS line profile across the section as well, where the 5 nanometer shows the relatively flattened and the continuous interface, while the 1 nanometer is show the EDS line profile indicating the platinum overlaps the nucleoside, the nickel element across the nickel element, indicating the element distribute from the interface, where indicating the nucleoside 1 nanometer is discontinuous, which is consistent with the Hartf image is here. And also we have studied the epitaxial of the nucleoside grow on the LSMO with different orientation. We have growth on the different orientation like the 001 and the 101 orientation. The theta to theta curve shows a single peak and clear single peak with nucleoside 002 and nucleoside 101. And also the diffraction spotlight show the single clear peak. And also the integration curve shows as relatively similar with the theta to theta curve, indicating the single crystalline with epitaxial growth on the LSMO. And the devices of the LSMO nucleoside and platinum, the 3 layers also shows a very flattened surface as well. Here we also show the Hartf image of the epitaxial growth on both orientation, where the 001 and 101 oriented. Where the nucleoside is quite continuous with 1 nanometer and clear and sharp interface obtaining as well. One thing to need to mention that despite the 70% that is mismatch between the LSMO and nucleoside, it could also achieve the epitaxial growth due to the misfit dislocation string relaxation. And we also obtaining the filter Fourier image as is below. It shows the red arrow indicating the dislocation, and we calculate the interface average dislocation spacing around 1.5 atom in the 001 orientation, and also the 3.8 atom in the 1.1 oriented. Then we also adding the 2 nanometer nucleoside on both orientation and measure the hard disk image. It shows that the nucleoside is quite distinctive and with a relatively clear and sharp interface as well. And also the EDS line profile across the 2 nanometer nucleoside image on both orientation, we are obtaining that the platinum is penetrate the limited distance into the nickel, showing the continuous nucleoside film. And also both orientation, the elemental distribution is quite identical. So there's almost there's a very quite similar chemical structure across the interface, regardless of the orientation. So the spin current transport difference shows stem from the orientation related features, such as atomic stacking symmetry, rather than the microstructure defects. So before to study the spin current transport, let me introduce some of the magnetic property of the nucleoside. The antiferromagnetic, the interaction is coming from a super exchange interaction mediated by the oxygen, performing the nickel oxygen and nickel bonding along the 100 the direction, for example, and the spin in the nickel and performing the antiferromagnetic alignment along the 101 oriented. And there's also the ferromagnetic alignment in the along the 101 plane. In particular, below the near temperature, we could induce the magnetic friction contract along the 101 axis. This could lead to the four equivalent, lead to the Romhedro distortion to performing the four equivalent T domains in this figure shown here. And also there's also the 3s domains in each T domains and separating 120 degrees as well. So totally it's performing 12 magnetic domain configurations. But also in our case, in the same film of the nucleosides, the twin domain structure will be reduced. The number of the twin structure will be reduced. However, it's quite challenging to direct probe the neo vector. Okay, so the relation between the neo vector of the twin domain and the spin polarization is quite important. When this both orientation is parallel, it could promote the spin current transport. In our case, the nucleoside 001, all of the T domain will obliterate from the spin polarization plane. And the nucleoside 101, one of the twin, the T domain will be parallel with the spin polarization. So it could promote the spin current transport through the nucleoside 101 orientation. And also, in addition, there's achieves a more complex interface in the 101 direction, which could to achieve the novel spin texture to increase the spin current transport again. So we are prepared 1 nanometer with this different crystallographic, where the 101 oriented shows the maximum inverse spin Hall effect voltage, and then the 001 oriented and the polycrystalline reach the minimum inverse spin Hall effect voltage, which direct pointing the relevant of the neo vector orientation to the spin current transport through the antiferromagnetic layer. So first, we are studying the spin conduction in the polycrystalline nucleoside. First, we need to prove that the polycrystalline or nucleoside have the antiferromagnetic ordering. What we do is to combine with a polymer and measure the exchange bias at 10 Kelvin, show the clear exchange bias, and the temperature dependence of the exchange bias value show the critical temperature. The blocking temperature is around 80 Kelvin, which is the blocking temperature is relatively lower than the null temperature. And also it's also quite difficult to direct probe the exchange bias with LSMO and nucleoside. So we performing these 3 layers, LSMO, nucleoside, and permalloy. We show the coercive field with the 2 step of the of the loop shape. And also before and after inserting the nucleoside, there's almost no change of the DC magnetic properties. So here we transfer the spin current transport process. Before study that, we measure the single LSMO. It shows a really similar resonant line shape with indicating the similar damping and very highly reproducible of the LSMO and high quality as well. And also we measure the LSMO nucleoside with 1 nanometer, the ferromagnetic resonance, so the symmetry curve, and also the inverse spin Hall effect shows almost symmetry with a negligible anti-symmetry component. And also in reversing the magnetic field, it shows the identical inverse spin Hall effect amplitude, which could exclude the spin replication effect and the thermal effect. So here we are studying the thickness dependence. We are adjusting the nucleoside thickness from the 0 to 10 nanometer, and we extract the amplitude and extract this. Here in this figure, it shows the maximum of the inverse spin Hall effect is shown at around 2 nanometer. However, there's no amplification effect compared with 0 nanometer. And also with increasing the nucleoside thickness, the amplitude of the voltage will be experienced exponential decay. And we also extract the spin diffusion length. There's two separation before and after 2 nanometer, where the above 2 nanometer have the relatively higher spin diffusion length due to the continuous of nucleoside thin film. And also we are inserting the STO with 1 nanometer as well, which has insulating non-magnetic layer. However, we show that there's almost no inverse spin Hall effect voltage compared with the 1 nanometer nucleoside, indicating the magnetic correlation is very important to transport the spin current. And also we are also studying the temperature dependence with 1 and 3 nanometer. With both sample, it shows the voltage have the monotonically decreased at the decrease of the temperature, which is mimics the platinum resistance versus the temperatures. Here we are going to study the spin conduction in the epitaxial of nucleoside. First, we are inserting, before I compare the DC magnetic property, before inserting the nucleoside, and after inserting the nucleoside, it shows there's almost no change of DC magnetic property. And also the exchange bias, where the 111 orientation shows the relatively larger exchange bias value than the 001 orientation. And we also extract the temperature dependence, where the exchange bias value disappeared at the similar temperature as around 120 Kelvin. And then we are studying the impact of the nuclear thickness on the damping and the spin transport properties. Here we are first extract the magnetic damping on the both orientation. And initially the magnetic damping is increased and then saturate with increasing of the nucleoside thickness. And here we show also that the nucleoside 101 orientation shows the lower magnetic damping than the 001 orientation. However, the delta alpha, the relative increasing of the magnetic damping is more pronounced than in the 101 than the 001 oriented. Where the delta alpha is, I mentioned before, is relative increasing of the damping relative to the reference of the LSMO layer, which is an indicator of the spin current transport through nucleus and absorbed by the platinum. And we can also adapt the delta alpha into the second equation and extract the intrinsic spin mixing conductance and the spin diffusion length. And by fitting this both curve, we can extract the both value on both orientation, where the intrinsic spin mixing conductance and spin diffusion length is more larger than the 001 oriented. We show that the 101 oriented of nucleoside have the more efficiency of the spin current transport. And if we think about the spin reflect on the nucleoside and platinum interface, we introduced the effective spin mixing conductance. And and this is the indicator of the spin current transmission efficiency as the interface as well. And the difference between the intrinsic spin mixing conductance and the effective spin mixing conductance is a spin backflow term. And here we show that spin mixing conductance is in the 101 is relatively larger and increasing more pronounced than the 001 oriented. And also the difference between the intrinsic and the effective spin mixing conductance is have the maximum value on both orientation. Show that the maximum impact of the interfacial spin loss for around 2 nanometer nucleoside thickness. And above the certain thickness of the nucleoside, as thickness, there's above a certain thickness, interfacial spin dissipation is saturated. So there have a balancing between the spin current, spin backflow, spin memory loss, and the spin current transport. It can be expressed by here in this figure. And finally, I will measure the inverse spin Hall effect voltage of the epitaxial nucleoside on the both orientation. Whereas the 001 and the 101, it shows on both columns. The voltage signal are fully symmetry, and they are, and also the by reverse magnetic field is inverse spin Hall effect is quite identical, which indicating there's no significant spin rectification effect and thermal effect. And also there's a really higher magnitude of the inverse spin Hall effect voltage in the 1-1 oriented. And also the line width is significantly broadening in the 001 oriented samples. And also we are studying the nucleoside layer thickness dependence, where the voltage value in the 111 oriented is nearly twice larger than the 001 oriented. And also the signal amplification effect is happening up to 3 nanometer in the 111 oriented. However, there's only 1 nanometer amplification effect in the 001 oriented. And also we are feeding the quasi-exponential decay with the thickness of the nucleoside. And it shows the diffusive spin transport through the nucleoside layer, where we extract the spin diffusion length of the both orientation is 2.3 and 3.4 nanometer, whereas the 101 oriented have a relatively larger spin diffusion length. Then we study the temperature dependence, where the 101 oriented sample shows the monotonically decrease at decrease of the temperature, while the 101 oriented sample shows the typical peak dependent relative with thickness of the neo temperature. The relative of the nucleoside thickness. So we can extract the peak temperature is the neo temperature with the relative with the nucleoside thickness from 0 to 3 nanometer is go to the linear dependence. And it confirms the side effect on the antiferromagnetic ordering. And also we can observe that is 1-1 oriented, the amplification effect have only around at room temperature, while the amplification effect is have a much more broadening than the on the 1-1 orientation. So finally, I will introduce my conclusions. First, we study the relevance of microstructure on the dynamic magnetic property or LSMO to study the twin domain boundaries in the LSMO STO001 film significantly increase magnetic damping. In contrast, the 1-1 oriented LSMO minimize the twin domain formation, making it more promising candidate for the spintronic application. And second, we are also studying the structure and the magnetic property of the nucleoside film. The epitaxial of the nucleoside can accomplish on top of the LSMO with atomic sharp interface and small interface morphology. And structure strain is accommodated via the interface dislocation and the antiferromagnetic ordering at low temperatures. And third, studies the spin transport in the polycrystalline nucleoside. The nucleoside grow at room temperature from the polycrystalline layer. For the nucleoside thickness less than 2 nanometer, the layer is discontinuous and allow direct contact between elasmol and platinum. And the spin conduction is primarily driven by thermomagnetic and short-range magnetic correlation. And finally, we studied the spin transport in the epitaxial of nucleoside, where the nucleoside epitaxial growth is achieved at the high temperature through the strain relief relaxation facilitated by the interfacial dislocation. And 1-1-oriented heterostructure exhibit significant improved magnetic and spin transport properties. And at room temperature, the inverse spin Hall effect voltage in 1-1-oriented sample is nearly twice as large as that observed in the 0-0-1-oriented samples. And 0-0-1-oriented sample, the inverse spin Hall effect voltage decreased monotonic with decreased temperature, while the 1-1-oriented sample displays a pronounced peaks that shift to higher temperature and decrease in magnitude as the nucleoside thickness increased. The temperature of the inverse spin voltage on the nucleoside thickness point to the spin diffusion limited transport mechanism. And the short value of the spin diffusion length suggests that the spin conduction is primarily governed by the thermomagnetic and short-range magnetic correlations. And the superior spin transport property and enhanced spin conduction in 1-1-oriented sample are primarily attributed to synergetic combination of the interfacial and dynamic effect, a more favorable neo-vector alignment and distinct interface symmetry. So our look is to also there's several key challenges and opportunities in the spin transport through the antiferromagnetic magnets. First, we need to further study the controlling the neo-vector orientation. Because the efficient spin current transmission in the antiferromagnets requires the neo-vector to be oriented perpendicular to the spin flow, and developing the reliable method to manipulate the spin neo order in the heterostructure is a critical step. Next step. So the second is to study the influence of microstructure and the crystallographic orientation. And crystallographic orientation, especially 1-1-oriented nucleoside, introduced the complex autotonic stacking and bulk interface. And this feature may enhance the spin orbital interaction or give rise to the novel spin texture, which is needed to further investigation. And third, there's unsolved mechanism of spin transport. As the fundamental process governing the spin conduction in insulating antiferromagnets remain unclear. Whether thermomagnets, evident spin waves, or antiferromagnetic fluctuation dominate is still debates and require further clarification. And finally, there's also the pulse of the spin current amplification. As the spin current amplification is observed in certain ferromagnetic, antiferro, and the normal metal system. However, there's an absence in others. So unveiling the origin of this selective behavior is essential for development of the next generation of spintronic technologies. So finally, I'll give the acknowledgement. I will be thanks to my supervisors, Professor Martinez and Dr. Matthelis, and also the ACM group in this figure, and also the members shown in this here, and also thanks to the services like the XRD low temperature magnetic service and the clean room, and also the list as below. And thanks, and again, and that's all. Thank you.
Thank you very much for the nice presentation. So do you want to rest a little bit, or we can go through the questions right away?
You can go through.
Okay, so first, Libertad Abad is going to ask you some questions or comments.
Hi, and thank you very much for your presentation. I think that this was very clear, concise, address a lot of questions that I have it when I reading your doctoral manuscript. I would like to thank you and for you and your supervisors for inviting me to serve as a jury in this dissertation. I believe that this thesis tackles fundamental aspects and technological aspects. And then I have two types of questions in order to solve some curiosity that I have it when I read this thesis. The first one, in fact, it was solved with the presentation because I like so much that you present your your defense with the first slide that you present. In fact, it's about power electronics efficiency because I missed this information in the manuscript, and I think that it's very relevant to give numbers in this point. But the second one, yes, this one. This is, I think that this is not in the manuscript, but I fully agree that this is important to present here, okay? But I have one, it's just a curiosity about the information density of this kind of devices. I mean, the flash devices based on magnetic materials or so on. In reference with the conventional ones. I don't know if you can explain me something about that.
Means the density of the storage.
Yeah.
It depends on the. Here we are show the spin current transport, and so the density of propagation it should be. Here we are not study quite more about the story density about that because we just study mainly about the spin current transport. And the density we need to change to another factor like the magnetic resistance, the switching magnetic resistance to the storage of the information. Typically in the report, we utilize the perpendicular switching to achieve the very low small size and more density of the storage. I don't know if my answer is answer your question.
Okay. Yeah. Thank you. In the other hand, the objective of this thesis is it's very clear, but I would like to go further and try to access if this material can be implemented in final device of systems, for example. I mean, recently the scientific community has very interest in find materials that compatible, I don't know, non-critical, low cost, green, and also materials that could be implemented or could be compatible with large scale production. In this sense, could you discuss where these materials could be implemented in devices, in large scale devices?
I think in this, as I mentioned here, we are in the preparation of the experimental, we are utilize the sputtering technique. In our sample, it's very small, but I think in the industry, the IF sputtering is very widely used, and it can be also achieve the large and integrate even with the silicon and achieve the industry as well. So the scale and the large scale the application is also can be achieved in this technology. Yeah, it's a kind of using the very famous and well industry utilized sputtering technique. I think so.
Okay, because you grow in top monocrystalline STO in principle, and do you know if this STO can be growth epitaxially in top the most used silicon substrate or something like that?
Yeah, as far as I know, if you want to adapt the silicon, we need to maybe to grow several buffer layer between that. So there's another further study to achieve the epitaxial growth on the silicon to adapt the utilization. Yeah.
Thanks. My next curiosity refers to the perimeter density of the boundaries, maybe in the page 89 of the manuscript. Is this picture?
Yeah. I understand. This is the calculation process of
Yeah,
the print.
Here is my curiosity, in fact. Could you please explain how you define this density and what's the physical meaning of this density and how you calculate and also the deviation, because if it's a graphical or a mathematical thing, how you calculate the deviation of that?
Okay. Use the software, the image software, Yeah, and for example, the sample D, we can check from eyes, we can get there's a twin, how to say, there's a two orientation of the boundaries. We can plot manually with twin boundaries in this figure, and we calculate the total boundaries length, and to subtract the squares of the image, and then we can get the perimeter density, and this can reflect the twin boundary network densities, and this quite relevant with our work because there's the dynamic property and so on. So it's arise from the boundary densities. So
thank you. And by means the manuscript and the presentation, I noticed that your films, your manganite films, in fact, are very, very thin. And I don't know if you have problems. Well, your manganite films and your, in general, all the oxides are very, very thin. You have not problems of the pinholes in these heterostructures?
Yes, initially, when I first do growth LSMO, it have some segregation even, or the roughness is really higher, or several particles. It depends on the growth parameters. Yeah, and also we also optimize as shown here. It put a lot of work of the optimization of the LSMO and utilize the off-axis to achieve the better DC magnetic property, and especially to use the silver paste glow at the interface very thinner to reach the better thermal conduction to reach. Yeah.
But the silver paste is only for the better thermal contact between the heater and the substrate, right?
In this here, yes, yeah.
And how you are sure that these films are conformal? Because I mean, for conformal that they are uniformly cover all the substrate. I mean, but because they are very, very thin, and you compare different roughness of different thin films, but I have not a reference of the substrate roughness, and then I don't know how you are how we can be sure that they are conformal.
Typically, the substrate is just from the commercial one, and from the easily processed, like cleaning by acetone, methadone, and stuff, and just achieve the very clear surface. We are also measure the EFI image of the single STO. It shows a very flattened surface, and not put, maybe I'm not put, I remember I put the manuscript as well. Yeah.
I didn't find, but maybe it is. No?
Yeah, it's so very flat surface, very well.
Yeah, very flat, but around the same roughness of the films? Or?
The number, for example, the STO, we are measured below 0.2 nanometer, and once we grow the LSMO, we measure again, it's also below 0.2 nanometer as well. So it's, yeah.
Okay. And yeah, and I have only one, I don't know if it's a question or it's a curiosity, because you study different thickness of the nickel oxide, but you not study different thickness of ICMAB in these heterostructures. Why? Just a curiosity. And if you increase the LSMO thickness, which one it's the effect, or you predict more or less which one is the effect in the spin pumping?
Okay. I think there's LSMO thin film is already well-known study. Here I remember I grows from 10 to 15 nanometer LSMO, and we saw there's almost no difference in this, right? Yes. The LSMO, the thickness is variable from 10 to 15 nanometer. For example, the DC magnetic property almost unchanged. So and also the why we choose this specific 15 nanometer due to the most study utilize that, and it's very convenient for us to directly utilize the spin injector to achieve the efficiency injector, because due to our sciences mainly focus on the studies of nucleoside transmission. So to achieve the reproducible LSMO is very important. So we just fix this thickness, keep the same condition, and just do variety of the nucleoside thickness.
Okay, then it's a choice. This thickness is a choice in order to have lower roughness or okay.
Yeah.
Okay, thank you.
Thank you. Thank you.
Okay. So thank you for the manuscript and for the presentation. So I enjoyed a lot reading this thesis, and in particular, like the order of the articles of the papers that you have presented. So one can clearly appreciate how the knowledge is being gained and increased. So you'll use the information that you extract from paper one to build up on this and go through all the papers. So it's also clear that there's a lot of experimental work and lots of samples and characterizations. So I would like to congratulate you and your supervisors and your team mates for all the hard work to produce these 4 papers and these theses. So as it's already published, I'm not going to question the validity, of course, of the scientific results, but I do have some questions, more out of curiosity of things that I did not understand. So related, now that we are in this, I take advantage of the fact that we are here in slide 16. So you have optimized some LSMO, and then you say here that the properties are the same for all the samples. Okay, so how can I explain, or maybe I'm not familiar, but if I see, for example, the part B of the magnetic characterization, the loops, I do see some differences. So when you see they're the same, what are the parameters that you're looking for?
Yeah, I understand. Yeah, thank you. The A sample shows much more different with other samples. So I would say that the sample A from the loop shape in the low field is different with others. And other sample is very similar, and this difference is much larger than the A sample. So I just say maybe.
Okay, so when you say similar, you mean the anisotropy field, or do you see the coercive field? You see these values?
Yeah.
Okay.
Yeah.
So also in this study, so and in particular when you determine with LSMO 100, then you have some twinning structures depending on the sample, right? So what does determine if we have one type of sample or another? Can I choose, for example, now I want sample A, or now I want sample E? So what is the difference between the samples? Is it the miscut angle that determines?
Honestly, the origin of to actually control the domain structure is very difficult for us. So we still a little bit puzzling of the formation of the twin boundaries, how to control that. For example, I said here, the twin density and the orientation is dependent on the growth parameters like this. And also the miscut angle is quite similar, but I don't know if it's real similar or not, or what else, or maybe a similar miscut angle. However, the real growth temperature is also different as well. But I understand, but I cannot give the direct answer to how does this control this.
So for now, let's say it's not controllable. You do the same process, let's say, and you achieve different results, and that's why you have to check every time. What kind of sample do I have? Is that correct?
Yeah, more or less.
Okay.
It's different.
So I cannot say, hey, Shulong, pass me a sample like sample A,
No.
because I want to study it. Okay, so it's just,
difficult to control the.
okay.
Yeah.
So for now, okay. I had another question regarding the same image that Libertad also asked about. So the one that you're analyzing the boundaries. So with respect to that, how are you sure? So what is the scale for these analysis? Because you know that SEM some images are local. So how are you sure? How do you make sure, or how do you do your study in order to make sure that this density that you calculate, do you calculate it with one image, or do you do a lot of images to calculate this boundary density?
I think due to there must be several errors when you calculate the twin densities. Here I put several the error bar to measure several times, to plot several times.
Several times with the same image,
Yeah.
or with different regions of the sample? I'm asking about, like, let's say
I mean
the likelihood of homogeneity within different regions.
The error is coming from the outline detectable from the boundaries, so there must be some errors. So I have to prepare one image with different times, and also several samples, different other. So utilize this method, and then others following this method. So we calculate the perimeter densities with all of the samples, and to extract the error bar and compare the relations. Yes, this.
Okay, but the area that you look for just one of the sample, the area that you look is an area like the one that is shown here.
Okay, yeah.
Is that it?
Yes.
Okay.
I show the paper here. This is the one of the, yeah.
Yes, but I was wondering, so here is one image.
Yeah.
I was wondering, in the same sample B, if I move like 2 centimeters
I understand,
away,
I understand, sorry.
do I have the same?
It shows the same. It should be the more or less
homogeneous.
Yeah, it's homogeneous.
The density.
Yeah, it's not like the here single domain and here two.
Exactly.
Yeah.
More or less like this.
Understand.
How can you be sure? So my question was, what was the study? So how did you ensure that it was more or less homogeneous?
Not understand previous. Now understand. We measure the SEM from the electron scattering model with the different regions, and prepare several images as well. Not only one, because here I only show one image.
Okay.
Yes, so it's still part. Yeah.
So is that how you obtain the error in this?
Also changing the
region.
Yeah.
Okay. Okay. I was surprised also when you do the optimization of the nickel oxide, and then you do the X-ray diffraction and the maps, the reciprocal space maps. And then you extract that you have a nickel oxide whose cell parameter is larger than the one from bulk. How can you explain? Maybe I'm not familiar with this too much, but I was surprised to see that the global volume is larger than the global volume.
Yeah, it's a totally expansion with 500 degrees to growth, and also in the room temperature and polycrystalline is also the enlarged of the sales parameter as well.
So I understand that in the direction where it is fitting the substrate, that I would have some tensile stress and would make him.
Maybe it's from the oxygen vacancies, it's from the nickel oxide and the increase of the lattice parameters. Yeah.
Okay, so you think
details, I'm not study so much about that because it's not quite. I just study the relief, the string relief between the in-plane and out-of-plane parameter difference. So I'm not quite study I am not the thing the lattice expansion I think is from the oxygen vacancies yeah.
so
Our
there are other studies. My question
defect,
was,
maybe defect.
are there other studies in which by doing some strain or some maybe maybe it's oxygen vacancies or whatever, are there other studies in which it is reported that the cell volume is increased with respect to the bulk value? Maybe you don't know.
I don't know.
Okay.
I'm not too focusing on this. Sorry.
Okay, just a curiosity. And so when you use in the second paper, the one that you optimize nickel oxide on top of LSMO, so how do you know what type of twinning structure do you have? So from paper one, let's say, how do you know? Do you do an optimization because the damping depends on the twinning boundaries?
Yeah.
So how do you know what you have? So for the other studies, you do a first study and then you show that the the boundary, the twinning boundaries affect the damping.
Yes.
For the other studies that you do, how do you know which type of sample A, B, or E do you have? Do you all through the damping? Do you do damping?
The studies I remember that and people using the growth on the sub STO001. There's performing a macrocrystalline string of the performing the twin structure, and it depends on the thickness. I remember the twin structure density. I mean the twin density network. You understand the density of the twin structure? I mean, people study the density of the structure. It depends on the thickness of the LSMO.
But
here no.
If you it's not the case.
Yeah. If you understand, ask case, I don't know what's your case. Here, you ask me the other studies of the twin structures. So
no, I ask you for the other studies in which you do heterostructures, you're using LSMO.
Yeah.
And in some of the cases, you use LSMO grown on STO001, such as this one. But we say that we cannot know which type of twinning landscape we have. You could have sample A or you could have sample E. In the other studies, I'm asking whether you check before doing the heterostructures, do you do an SEM image or do you just ensure that the damping is the same? Do you do something to know which is your kind of sample?
I will say that actually in the real measurement, we are first to grow the LSMO and then to measure the magnetic DC magnetic property and stuff, and also measure the SEM from the electron backscattering. This is the sample one, sample to sample, as we are also keep the samples and to compare. I don't know where's the.
Okay, don't worry.
I don't understand your question. Sorry.
Okay. I was curious also in this same paper, why you chose in the final structures, if I remember correctly, you chose 1 nanometer of nickel oxide, whereas all the characterization that you have was either with 25 nanometers of nickel oxide or 5 nanometers. So why is that? Why is that the choice? And did you try with 5 nanometers?
You mean which measurement? The
in
here?
When you do the optimization, I think of nickel oxide.
Here is 5 nanometer. Just a second. Yeah, polycrystalline nickel oxide is measured in bias. The epitaxial?
Yeah, no, I don't remember.
Here's the epitaxial with 5 nanometer to measure etching bias.
Okay, so maybe I understood incorrectly. No matter.
Okay.
So can you go to the one, the epitaxial that you just showed?
This
No, next. No,
epitaxial structure, right?
no, sorry, no. Two before, you have passed it. Okay, no,
I don't, which page? This is 22.
I had a question. I'm not sure which was the slide. I have not noted it down. Okay, whatever. I will ask about this slide that is here. So I would like to understand with this and with the non-epitaxial, so the polycrystalline, can you help me see the heterostructures in order to know what is this? For example, in image D, I can see a sort of line between nickel oxide and platinum. What is that? So I'm wondering about the interfaces between nickel oxide and platinum.
Here,
Have some kind of nickel platinum alloy, or I'm not so familiar with these kind of SEM images. So I was just curious about the interfaces, both here and in the one that you say that it's discontinuous and I don't see it, but I'm not trained. So maybe can you help me decipher how the SEM images are?
this we will compare the four figures. One is 1 nanometer on both orientation and 2 nanometer on the both orientation as well. This is visualize the interface. We show that the LSMO nucleoside here, we can see a very clear sharp interface, and also we are measure the EDS line profile. This is important for us.
Yes, yeah, I understand that. But why is it that in image D, I can see a sort of black line in the nickel oxide? And why is it bright underneath? Do you know?
This is because of the tuning the contract, because the atomic number is, we have to tuning the contract. So
you have changed the contrast,
yeah,
right?
The contrast change so different.
But the contrast, you have changed it for the whole nickel oxide layer, right? Not just for the interface.
I think this.
I'm just wondering if you have
maybe
why do I see an interface that for me is not completely, it's abrupt. So I have no discussion about this, but I don't understand what is the white line and the black line at the interface. I'm wondering whether you know what it is.
This picture may be combined, is automatic combined because it's more convenient to tune. First, it's not changing the contract, so the interface is shows very clear. If it's real measurement, the interface is not going like this. So just tuning the contract. And regarding the dark interface, I think it's also due to the changing the contrast as well. And some you can see some different of the I think this, and also I said before, there's also 77% on lattice mismatch of the nickel oxide and LSMO. So it might have some dislocation. And also measure the here's the dislocation spacing of the nickel oxide and LSMO interface.
Yes. I understand this. I just don't understand the STM images. I have trouble like seeing where a layer ends and one other begins, and why we have some white or black lines.
Yeah. The result we are not a direct. How to say? So this result is just to give an intrinsic. How to say, the intuitive picture of the interface.
Yeah, and it does not modify your conclusion. But I was wondering what was the line and if you knew what it is. And can you go to the non-epitaxial part, the polycrystalline one? Because you say there are some parts that are touching this one. There are some parts that are touching each other. So in the element analysis, I can see, but in the STM images, the nickel oxide, I cannot see clearly. Why do I have, for me, I can see three regions. One regions of the atoms that are perfectly following the LSMO, one region which is blurred, gray, and one region which is white. And then comes the platinum, right? So for me, I do not see the platinum touching the LSMO. So I was wondering when you say, it's clear that we have some parts touching. So at least from this image, I cannot see it. Maybe it was in another image that you could see it. And I was just wondering, these 3 regions that I see,
This region,
am I seeing it correct, or I don't understand the STM
yeah, I
image?
understand. This image is just to clarify. Here is the nucleoside. The interface of the nucleoside and LSMO is not quite continuous. Not we cannot see because the resolution is still limited. We can see the red here just show that the nucleoside is discontinuous, not flattened interface. That's all, and
Okay.
not so much from the image. Yeah.
Okay.